everyone. Welcome back to the GGM YouTube channel. So last week we did some stars and bars, which is a decently advanced combinatorics concept. This week we will be starting something a little bit different. On the channel we'll be regularly cycling through concepts. So this week we'll be doing sort of an introduction to geometry. So this week might be a bit basic, but next week we'll have more complicated problems for you to solve. So if you feel like you already know most of this stuff, you might not need to watch this, but this is just to get you familiar with the fundamentals. So what really is geometry? Geometry is the study of the properties of space, and in this class we will be mostly covering two-dimensional shapes and lines. So if we draw a straight path between 2 points, we call it a line segment. The 2 points are called endpoints. If we have a straight path which goes infinitely in one direction, but has an endpoint in the other, we call that a ray. If we have a straight path that goes infinitely in both directions, it's called a line. And any 2 points can form a line, and moreover, any 2 points will form a unique line. So if we consider our flat plane, right? Or let's say you take a piece of paper and you draw 2 points. Those 2 points are just going to create one unique line. You can't draw a different line that goes through those specific 2 points, right? And 2 lines that never touch or intersect at a point are called parallel lines. So 2 rays that share an origin form an angle. And the rays are the sides of the angle, and the origin is the vertex of the angle. So basically 2 rays that share the same point that they go out from, right? And we measure angles as fractions of circles, where a full circle has 360 degrees. So for example, if we have an angle that is 1/3 of a circle, we say it is 120 degrees. 90-degree angles are right angles. So you might have heard of this before in the context of right triangles, perhaps. And 2 lines forming a right angle are called perpendicular lines. And as you'll see, right angles have some special properties that translate over to triangles. And any angle below 90 degrees are called acute angles, and angles between 90 and 180 are called obtuse angles. There's also angles over 180 degrees, and they're called reflex angles. Usually you will not be working with these, because really when you have 2 rays that share an origin, you're forming 2 angles. You're forming the angle, a smaller angle, and you're forming a bigger angle. Or if it's just a straight angle, both sides are 180 degrees, that's fine too. But when you have these 2 rays, you have these 2 different angles that you're forming. And they're going to add up to 360, of course. But one of them is going to be a reflex angle, and usually we're going to be working with the angle that is not the reflex angle. So extending this, angles have a close relationship with parallel lines. So consider the following diagram. So let's say we have 2 parallel lines, as you can see here, and we have a third line that is crossing these 2 lines. This is called a transversal, by the way. So angle x, so you can see that's bounded by the transversal in one of the parallel lines. Angle x is equal to angle y because there's something called vertical angles, or angles on opposite sides of the intersection point. So vertical angles are always equal. So you're going to see x and y, they're the same, right? And intuitively it makes sense, right? They look the same, right? And angles y and z are also equal because they lie on the same side of the transversal. So you can see they're on different parallel lines, but they're still on the same side of the transversal from the points of intersection. So y and z are congruent, or equal. We'll get into that later. But these angles are called corresponding angles, and they're always equal. And because y is equal to z and z is equal to w, because again they're vertical angles, so we can say that y is equal to w. And y and w are called alternate interior angles, which can be very useful in certain proofs. but these will always be equal. So x, y, z, w, all four of these angles are equal to each other for various reasons. So with all of that out of the way, you might be wanting to get into actual shapes. So triangles, we'll start with that. So triangles are shapes with three sides. I think you probably know that already. And there's three angles. So, I mean, that's why they're called triangles, right? Try three angles, right? And triangles are the least number of sides a shape can have, right? You can't have two-sided shape. It doesn't really work like that. And they have some special properties. So the sum of the angles in a triangle is always 180. So I'll just give you 5 seconds to try to prove that for yourself. Okay. Hopefully pause the video and try to solve it. So if we have some triangle, let's say like this, right? We'll call the vertices A, B, and C. So, okay. So we want to prove that all these angles, these three angles, we want to prove that these add up to 180 degrees. So how are we going to do that? Well, we can start off by drawing a line through this vertex, right? That is parallel to BC. So we use this notation to denote that these two lines are parallel. And from what we just learned about alternate interior angles, we know that we can see that this line segment is the transversal of these two parallel lines. And something we can notice is that this angle right here, this is equal to angle C, because they're alternate interior angles. And for the same reason, this angle right here, that's equal to angle B, because they're also alternate interior angles. And then you just have angle A here. So as you can clearly see, because this forms a straight angle, right? This is just comprising the entire straight line. That's 180 degrees. But that also happens to equal C right here, right? This is C plus A plus B, right? So that's how we prove that. The exterior angle of a triangle is formed when we extend a side of the triangle past a vertex like so. So as you can see, one of these sides is being extended, right? It's becoming more of a ray over here. So the exterior angle theorem states that the exterior angle of a triangle is equal to the sum of the other two interior angles. So I'm going to give you another 5 seconds for this one. Okay. So if we're back to this example, let me just draw another triangle. Sorry, my triangles aren't exactly the most straight things, but we can deal with that. Okay, so let's say we're extending this over here, right? So this is C, and then we're extending it over here, right? Let's say to some point D, okay? Okay. So what we want to prove is that this angle right here, angle DCA, 1 second. We want to prove that this is, the measure of this, right, is going to be equal to what? The other two interior angles, right? Because this is the exterior angle of angle C. So we want to prove this is equal to angle A plus angle B. And something we can notice here is first we know that 180 degrees is equal to angle A plus angle B, right, plus angle C. And however, from this, we can also see that BD is a straight line, right? BD is a straight line. So if we have angle DCB, That's obviously going to be a 180, right? Because it's just a straight line. It's 1/2 of a circle is another way to think about it. So now something you could do is just say, well, this is also equal to angle C, right, plus angle DCA. And we already know that 180 equals angle A plus angle B plus angle C, right? So these two have to be equal to each other. Alright, so now we can get to some areas. The area of a triangle is simply 1/2 times the base times the height. The height of a triangle from any given vertex is the line segment that starts from that vertex, hits the opposite side. Oh, I'm sorry, by the way, vertex is the plural, so vertex is the singular, so all these should be written as vertex. Sorry about that. So from any given vertex is the line segment that starts from that vertex, hits the opposite side, and is perpendicular to the opposite side. So as an example, the height of the triangle ABC from A is AD. The base of the triangle is just the opposite side of the vertex. So the area of ABC is 1/2 times BC times AD. And always remember, because AD is perpendicular to BC, that means it forms a right angle with BC. And just to explain the formula a little bit, since a rectangle's formula is just the base times the height, for any triangle, if we draw lines from the vertices like so, we can draw a rectangle around the triangle. And clearly the base and height stay the same, but if we cut the triangle into 2 halves using the altitude, we can see that on both sides, the triangle area is just 1/2 of the rectangle on that side. Therefore, for the whole triangle, it is just half the area of the rectangle. So you can see that this right triangle, right, on the left is 1/2 of the part of the rectangle there, and the right triangle on the right, which is a little bit weird, is 1/2 of that part of the rectangle. So overall, the triangle is just 1/2 of the base times the height. Okay, so congruence. Two triangles are congruent if they are exactly the same in every single way. So that means all the corresponding sides are equal to each other and all the corresponding angles are equal to each other. So if we have two triangles ABC and DEF, if AB equals DE, AC equals DF, and BC equals EF, we can say the triangles are congruent. So this is actually one type of determining congruence. We have SSS congruence, which is what we just used. So if all 3 sides of a triangle are congruent to all 3 sides of another triangle, so if triangle ABC has sides 3, 4, 5, and then DEF also has sides 3, 4, 5, the two triangles are congruent. So all 3 sides equaling each other will guarantee that all 3 angles also equal each other. We also have SAS congruence. If 2 sides of a triangle and the angle between them are congruent to the 2 sides of another triangle and the angle between them, the 2 triangles are congruent. So if we add something like AB equals DE and AC equals DF, and then we had something like angle A is equal to angle D, that would mean the 2 triangles are congruent. So remember, it's always the angle between them. It's not just some random angle. If we have these 2 sides that are congruent to each other, these 2 corresponding sides, the angle between those 2 sides for those 2 triangles must be congruent. Otherwise, it might not work. And we also have ASA congruence. If 2 angles and the side in between them are congruent, the 2 triangles are. So it's much the same as SAS, except this time it's 2 angles with the side between them. And similarity is a very similar concept, and it's when 2 triangles are the exact same except one of them is larger or smaller than the other. So the angles are all congruent, all angles are preserved, but the corresponding side lengths all share the same ratio. So they're not the exact same, but they share the same ratio. So if ABC is similar to DEF, that means AB over DE is equal to AC over DF is equal to BC over EF. and we have SSS and SAS similarity as before. If all the sides are in the same ratio, so if this ratio right here is satisfied, the triangles are going to be similar. Or if we have two sides in the same ratio and the angle between them is congruent, the triangles are also similar. And one last thing, we also have AAA similarity. Since we only need the angles to be congruent, if all three angles are congruent, then the two triangles are similar. So you might have noticed that there is no ASA similarity on this page. Why do you think that is? I'll give you 5 seconds. So the reason there's no ASA similarity is because if we have two angles, we automatically know what the third one is. So if we know that angle A equals angle D and angle B equals angle E, because 180 is equal to angle A plus angle B plus angle C, we know that angle F is equal to 180 minus angle D minus angle E, which is also equal to 180 minus angle A minus angle B, which is just equal to angle C. So we will see that those two triangles are congruent. So we don't need the side, we only need the angle, so the S is unnecessary. There's also something called the triangle inequality. It is an extremely important inequality for geometric proofs. There is an inequality stating that if we have a triangle with sides A, B, and C, the sum of any two sides must be greater than the remaining side. So A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A. Think about this. What if we have three lines where one line is greater than the sum of the other two? Can we make a triangle with them? And moreover, what if the line is equal to the sum of the other two sides? Can we make a triangle? So the answer here is actually quite weird. So I think most of you will be able to recognize that if you have, let's say, line A and then line B, line C, and let's say line A is greater than the sum of B and C, right? So if we put B here, right, let's say that this is where B begins, right? And this is where B ends, right? And then this is where C begins, this is where C ends. You can see that even in the best case scenario, where the ends are as close to each other as possible, they're not going to be able to get to each other, basically. So they're always too far from each other. They can't form anything. But if angle A just so happens to be exactly equal then to the sum of the other two, then we have a very interesting scenario. So this whole thing is going to be A, and the only way for B and C for their ends to meet at the exact same point is going to be if they're lying on top of A, just like perfectly on top. And you're going to see that this is just a straight line. So that's what a degenerate triangle is. It's just a straight line, and it's just a line segment, basically. So next week we'll go over more triangle formulas, and we'll explore triangles a bit more, and maybe even circles. Thank you everybody for tuning into this class, and I hope to see you next week.